Because hello guys, so I am now on a laptop. We have lost power in the classroom and I'm not sure if the computer is going to come back, to be honest. That's what's going on. So I'm gonna go ahead and, oh, that's a great shot of me. Can't even see me. Not hearing anything, turn up volume. So I'm gonna go ahead and why don't we do it this way? I'm gonna email out the group work to you. And you guys work on it. We'll see if the equipment comes back. If not, I will get to teach from this device. So that's going to be a lot of fun, especially since I don't think the pen works on it. Yeah. Also, a couple of other things I'd like us to consider. First item for consideration is we moved the solids class, the fluids test, and folks would like us to move the solids test as well to next. So instead of next week, it would be the week after. So let me know if that works for you.
Yeah, that's right. So it's the WY, the force on the board times the length for the L.
All right, party people. You now have, I've just emailed you as a group, the group work if you want to get started on it. As I said, we will see if stuff comes back. I might have to call IT and see if they can come over. I can teach from my laptop. The problem is that the folks in the classroom, oh, hang on, it looks like things are returning, won't be able to see it.
That's it. So since volts are taking force. So yeah, so it'd be divided, it would be two, it'd be divisible by two. Then it would be divided by two, and then we're only finding 1 volt. So really, it's only a quarter. Oh.
Yeah, you guys can work on the whiteboard if you want.
Other back house.
Calculator on the whiteboard.
Oh, we left this calculator on the whiteboard. Yeah, go get it.
So force is coming, right? Yeah, the force. Which is 667.
Recording in progress.
So it'd be no inertia. For-
Check.
And that's. Cause it's.
Okay, so,
T color class.
Gibran, you came back in. We lost power here for a few minutes. So, power is back.
Is they.
Smart board. Is the smart board back? Smart board is back. Cool. We are good to go. I don't know why it's beeping. That's always very disconcerting when it starts beeping.
Since only bolts 1 and 3 experience the force of the wind. Half that force. Can you goes to each one of those bolts.
She sends.
So then you divide.
Actually, I don't have I didn't have to turn the camera back on. I'll turn the camera back on in just a moment.
Area. Shear stress. It's. Diameter of the bolt times the thickness of the plate. Bingo, alright. So there.
Did you find it?
Yeah, we're good.
Really good problem.
Times thickness.
I'm just going through it.
Let's see. So we have the diameter.
Um, 625.
So it doesn't give us the thickness of the plate though. Say T is thickness of plate. Clear it.
So it'd be 24 T. Well. Cause I did over 2, you did 0.5.
So it'd be two of these though. It'd be both of the plates though. So we'd have to like be careful and say like thickness of one plate. Or thickness of both plates. 2T.
Let me know in the chat, did you guys get the email?
2 times the diameter. There's 2 bolts taking that.
So 2 times 12 times 2 to the 2T.
It's, I think, yeah, it's like over the area. So that's all.
2D. 2T times 2D2. One, 2 on the bottom.
I think that's what they accounted for.
So I think it would be.
Oh,
All right, so it looks like you guys got the email. I think that's probably the best way to share it. Gibran, did you get the email?
I think no.
Yes, I did.
All right, excellent. And I'm assuming now you can see me, is that correct?
Yes, as you can see.
Excellent.
So why?
Everything is slowly coming back online. Hopefully we don't get another bump.
Because for shear stress. And the area. It's time.
Did you guys both pick them up?
Both come up and then I emailed them
2 plates.
Yeah,
Right.
it's just part to
Okay, I dig that. Sorry, because. When we're talking about shear. You wanna know. Yeah, I think that's right.
Advanced statics?
Yes.
What's the prerequisite? That's the problem.
Probably because you didn't take it here.
Yeah. That's good.
Oh, yeah, that's actually, honestly, that's probably it. And did you transfer over your,
I'd say, I think it's just the fact that we don't have.
transcript or anything? Don't bother, it's gonna take too long.
Just help us get it through.
And you probably need the same thing, and you are the infamous Brock.
That is me.
When she said, I have hearing aids, but when she came in and said, oh, I brought Robbie and Brock, I heard Robbie and Rock, and I'm like, we're now bringing rocks to class.
I mean, I got a rock
That would
in my bag.
Yeah. Mine, we have rocks on us.
I bet you do.
No, I actually have a bag in the back of your car.
Oh, yeah.
No, I'm not kidding.
Okay, the rock bag.
I have stuff from mine
Jesus,
too.
all right,
Yeah.
that's cool.
Your coefficient, the variables.
And then do we need the statics weight for both 219 and 230 or just 230s?
What'd you get?
I don't know, we'll start with 230.
Sounds good.
The only class that,
Well, gee, that would be- Yes.
the only class I care about is 230, I mean, from a static standpoint.
Yeah.
Right, we don't use a lot of statics in fluids.
I don't know if one of those.
All right, good, Ellie, check your email, there's group work in your email.
Oh, this is what I got, I'll send that in. I'll send
That
it
you-
to 667.
About quiz on you.
5 or over 0 to 18.
Oh, shit.
I'll send it. Oh, I did that too. So.
No. I mean, if you want it next week. I can read tomorrow, you can take it.
I bought like 3 of those chargers.
I'm gonna keep with it.
I don't know. No, it's like I'm trying to borrow it. Just steal your chargers.
I can bring it tomorrow, you can just take it for a minute.
We need to charge your girlfriend like maybe once a semester.
Dude, now it's like 11 years old, it dies every week. I remember this. The one with the 667 there, solar solid. Which is the force for bolt one, so the intention one. What was it?
It's 6 and 3, -6.
Thank you. 1,000 kilopascals.
This. It's This?
Yeah.
Yeah, go for it, I mean, I did them.
What's your coefficient?
This is. Round. No, that one's wrong, but this one.
Then 1,473. This is gonna be.
It-
That round.
You have to
This
convert
is
it
667.
because it's.
I know.
It's just right to. It's right to a point two five.
I'll try.
This is Thank you.
Oh, good, Raul's here. Raul, check your email, I emailed your group work.
Because this is.
Alright, I'm gonna call attendance and then we can talk about these problems.
So I.
Use 12.
It's
If you would.
2 bolts,
2T,
I can't do
two
that.
plates. The IR squared.
And other things that have been brought up.
That's
You guys are having too much fun over there. I will have to separate you.
No,
No, you're not having any fun at all.
never.
Good.
not today.
We are engineering people. We do not have fun.
Squared to two.
Two black box.
We just drink hard and party harder.
This two. Sounds right.
Where I went to school in the dark ages with the dinosaurs,
Yeah.
the second
So, okay,
verse of the school
that's-
song was,
Two plants.
give me a barrel of rum, sugar 300 pounds, a bell to put it in and a clapper to stir it around. I am an honest fellow. I drink my whiskey clear. I'm a rambling wreck from Golden Tech. I'm a hell of an engineer.
My student.
What'd you say?
That's like a typical my student thing.
It was. The third verse was even better. If I had a daughter, I'd dress her up in green, send her up to Boulder to coach the football team.
Well, hold on.
But if I had a son, I would tell you what I do. I don't remember the next part, but then he'll go to mines like his own man or something like that. So,
Still about fresh.
I'm just gonna leave it like
I
that.
trust you more than I trust myself.
nobody trusts Tyler.
Definitely not.
I trust.
I like doing it.
With your kids, maybe?
Maybe not.
Mom, but
Don't know.
would you trust me with your kids?
Determined.
Great conversation.
You get that from me.
Care about everyone's life.
Hey, I save life.
Just
I promise
everything.
you.
Was
It's
hard.
literally in the mission.
And I'm gonna go ahead and take attendance.
Would you, what,
Being a geology
I don't know about
major.
that.
I don't know.
So Tyler, you're here.
Yep.
Simon, you're here.
Yeah.
Ebron, you're online.
I,
Raul, I thought I saw you come in. Are you online?
You guys got too much, right?
All right. Kay is here in the room.
I am.
Declan. Declan, are you online or are you at band practice?
Oh, I forgot
You
squared
literally
in
just
here,
do
dude.
the pendulum.
Squared. Good, I got it.
Yeah.
Right.
Sol, are you here?
Too much.
I don't think it's,
I don't know what I'm doing.
Hussein, are you here?
I've not started these problems yet. I was really hoping you.
Michael.
Fact that it doesn't.
Austin. Austin is here. Melody is here. Ellie, you're online today, right? We're not even doing a bingo today, Ellie, and you're still online. Amelia is here, Jose is here, and Alex is in the classroom. Okay.
This is. Stress, so we need to take out from this equation of the plates.
And those of you that are online, can you now see my screen?
What's left is the area of the hole.
Okay. Ellie's dog is still sick.
That's the higher minus. So if it's shear stress, you're calculating the area that will shear. So actually it would be the 2 volts on both sides.
Okay, so online people,
2 piece cotton.
I don't want coffee.
Okay, so it's.
I have, I actually bought two.
inclined people, stop talking. Online people, because I need a consensus on this. So I have been requested to push this exam out by a week because they're freaking out because you guys are engineering students and you're overwhelmed and you're freaking out because that's what you guys do. All right,
Look,
true or not true? I need to fix the camera.
very true, absolutely true.
All right,
Push it back until the end of the semester.
well, we can't do that because you don't want all the problems at the end of the, I lost my camera settings with that whole little
That would be
fiasco.
terrible. One test,
Having one test, yeah,
just on everything,
on absolutely everything.
Pass or fail.
yeah, pass or fail.
Yeah, it sounded worse by the minute.
Legit.
Okay. All right, so I am willing to do that. If that makes you more comfortable. I am gonna start it on chapter 2 today, and then we will see where we are. All right. So Austin will be driving on the 25th. Austin, so you're leaving on the 25th to go someplace. If
Yes,
you're gonna
yes, I
take
am.
it virtually, right, Austin, I assume?
That was the idea, yes.
Okay, so I can just open it up earlier for you. Would that be okay?
That's totally okay with me as long as I'm I'm able to take it because I won't have signal on the 25th.
That's fine. So you won't have signal on the 25th. When are you leaving town? Because let me back up. Were you going to take it virtually or in person?
Virtually, but I can take it in person if you prefer.
Not necessarily, as long as you don't cheat.
Okay.
Okay, so I'll go ahead and I can open it up for you much sooner if you like. In fact, that's not a problem. All right, just let me know
Okay.
send me an email, tell me when you'd like to take it, and I'll open the virtual exam for you. Just don't tell your classmates what the problems look like. So Gabron, yes. Initially we were talking about having
Thank you.
fluids. You're welcome. Fluids. I don't know about dynamics for next week. But fluids and solids next week. I don't know. I'll have to look at the dynamic schedule. So we're gonna go ahead. We will do solids on the 25th. Okay. All right, yeah, I'll need to fix the attendance at the end. All right, so let's go ahead. What I think I'm gonna do, well, maybe not. Let's go ahead and talk a little bit about what's going on here. Okay, and how this is going to, for lack of a better term, how this is going to work. All right. So what's happening here is we have a what did they call it? A removable signpost. All right, for hurricane evacuation. All right, part A says find the average shear stress at the bolts 1 and the bolt 4. All right, so when we're talking about shear stress, what are we talking about? What does the stress look like when it's shear stress?
Perpendicular to the.
It's gonna be perpendicular. Oh, Ellie wants them staggered. Okay, so Austin, I'm happy to open it up early for you so you can take it before you leave town. Hopefully you're going someplace cool. All right, so we want to figure out what's happening in bolt 1 and bolt 4, and we're going to use the shear stress to do this. Now, what is our equation for shear stress? Force over area, right, of the bolts. Okay, now, if we think about it, Wy is my shear stress, isn't it? We all agree? And we're given what Wy is, but how many bolts are dealing with Wy that we're looking at?
2.
2. So we're gonna make the assumption that they're gonna split that force. Okay, so my force in this equation is then gonna be 667 divided by 2. Run a number for me on that.
That's gonna be 333.5.
Hey, that makes sense. I probably could have done that.
Yeah.
All right.
Yeah.
Area of the bowl. Sorry. Area of the bowl is then gonna be pi. We usually talk about it in R, but it's going to be diameter divided by 2. Now, squared, we're making an assumption here. We are making the assumption that the bolts are all the same size. Right, and the diameter we're given for the bolt is 12 millimeters. So this is then going to be pi times 12 over 2 squared. So pi 36 comes out to be what?
$36 133.97.
All right,
0.97, sorry.
113.
And I'm all over the place. You're right. You might as well just erase the whole number.
113.
let's try this again. What is the number?
113.097.
All right, so my tau is associated with the shear stress, is then gonna be 30, I don't know what that is then gonna be 3.5 divided by 113.097. So that's gonna be what, 2 and some change?
So since we divided the force between the two bolts,
Yeah.
we only have to take into account the cross-sectional area of one bolt.
Right, because what we said was happening was the 2 bolts are splitting the force.
But it-
Okay, so by doing it to start with like this, there's 2 ways we could do it. One way is we would leave the force as 667 and then split it among the 2 bolts.
And then there'd still just be a 2 in the denominator.
Right.
Okay, cool.
Right, you could do it, you certainly could do it either way.
Okay, cool.
So what do you come up with when you do this?
2.95.
2.95? All right, so that is our shear stress. What I did not give you, you're missing a diagram.
That'd
All right, that what?
be millipascals, megapascal?
Megapascals,
Okay.
because we divided by millimeters.
Okay, that always throws me.
All right, so let's talk about what's happening here. All right, because if we look at this as a sideways with the lower, so we've got the lower anchor post and upper anchor post. This is a blow up of this right here. So if we look at it, right, this is gonna be what? I believe we have 1 here, 4 here, 2 here, and 3 there. We double check this diagram here. 1, 2, yeah. Okay, the problem we're having here is these are the 4 bolts that we're seeing. But when shear stress comes in, who is going to see the shear stress?
with the bolt.
Right. So it's gonna be bolt 1 and bolt 2.
Thing in the, it says 1 and 3 are the ones taking.
Oh, it says, oh, I put these in wrong, didn't I? Right, it's because the other ones are behind. All right, so 2 and 4, what is gonna be the shear stress on 2 and 4?
0.
0. All right, so
Says. Okay,
it says so.
It's just always 0.
the hole there. Well, no, it's because the two
No,
bolts
it's
are right
because
here.
those 2 front bolts. All right, so tell you what, Kate, you do this all the time in the other class. What happens if you lean your chair back?
Don't fall.
Okay.
Mine's pretty good.
But if you, instead of going from 4 legs on the chair, you're only going to 2 legs, right? So then those front 2 legs are no longer seeing any force on them. All right, so if the shear stress is coming in,
Okay.
all right, so the shear stress is coming in like this, these bolts here are gonna see what's happening. The back bolts aren't gonna see that shear stress. Cause they're the ones that are taking the stress. Does that make sense at all? Brock is giving me a look like I'm crazy, but he hasn't had to deal with me yet ever in his life. So everyone else just assumes I'm crazy. All right. Okay. Now, let's talk about the bearing stress.
So 1 and 3 have 0.
Yeah, because only 1 and 2 are going to be resisting the wind force. Or 1 and 3, I'm sorry, are going to be resisting the wind force. 2 and 4 are not seeing it. Okay. The second part is we want the bearing stress. What type of stress is the bearing stress? Okay, it's a bearing stress. Okay, that's fine.
Bearing stress.
But is it a shear stress or is it a normal stress? It's gonna be a normal stress. Okay, so we're now gonna need to do this calculation. Right? Once again, we only have 2 bolts. I guess this, my solution says 1 and 2. You guys say it says 1 and 3?
Yeah.
Whatever, it doesn't matter. We're gonna have 2 bolts that are going to be dealing with this, correct? What are the 2 bolts that are gonna be dealing with it? Yes,
2 and 4.
no,
I'm so confused there.
okay,
It'd be 1 and 2. Or whichever.
One and
let's
three.
just back up just for a second. Let's say I have a box, right? And I'm putting in the shear stress this way, and I'm putting in the normal stress that way. All right. This part, this corner of the box, and this is a little different from statics in the sense in statics, we don't worry about where those forces are acting. But in this one, we are going to worry about it. So what's going on is the stresses, those front bolts are seeing all the stresses, both the shear stress and the sigma, which is our normal stress. Okay, so it's seeing both of those. You can also look at the sigma as the axial stress. Yes, when they talk about bearing stress, they're talking about the axial stress. And that was the whole divided by 2 thing that you guys got all confused about. And then I took a picture in Mexico. So we have a bolt, right? And the bolt is going through this. So our sigma or our bearing stress is coming in like that on our bolt. The shear stress is coming in this way.
That makes sense.
Okay. Irregardless of the number, we have 2 bolts. So we can either divide it by 2 because they're both sharing it after the fact, or we can start by dividing it by 2 before the fact. It's the same W sub Y. So our force, we're back to that number, what was it, 333.5? Okay. All right, but let's talk about what's going to change is the area is going to change.
You're just looking at the bulkhead.
Okay, we're not looking at the bold head. We are looking for no sighing allowed.
Yes, I.
Who sighed?
Not me.
Okay, we are looking for, it was Simon, I know. I'm looking for that area.
So it's the diameter by the plate size.
Exactly. The area is going to be the diameter times the thickness of the plate.
So we talked about this.
Don't they give us thickness?
No. I don't think so. They gave us the bolt diameter.
If the bolt diameter is 12, due to 14 millimeters. I don't know, maybe I didn't give it to you.
Yeah, that's right.
I didn't give it to you. All right, that's fine. It's gonna be 14 millimeters. It's not fine, but. So the thickness is 14 millimeters and our diameter is 12 millimeters. So multiply those together, what is that gonna be? According to the notes, it's 168. Is that what you guys get?
168 is good for me.
168 millimeters squared. All right. So the bearing stress is then going to be 333.5 divided by my 168, and that's then going to equal 1.985.
Yeah.
You guys said yeah really quick. Megapascals. Okay, all right, so let's do quick, let's do a quick summary of this problem, and then I'm probably gonna go ahead and dive a little bit into chapter 2, because I don't want us to get we're already behind, but then we'll get even further behind. And I'm gonna send the rest of this home with you. Is that okay, or is that gonna freak anyone out? Simon's drinking tea, he's having such a bad day. All right. In addition, your sample exam is, I have it with me. So, but it's only chapter, so. Bearing stress, okay. That is the exploding inside-outside pipe. Okay, there is a problem. No, you can do that one. Yeah, okay, so there are 7 problems on here. You will not have 7 problems on your exam. But I believe that exam, the sample exam is just chapter 1. Let's do a quick summary on this because the equations don't change, right? If we are talking about shear, then we are talking about the area. This is what changes. The area is then going to be our diameter. Right? Because why? We have a bolt. That's the bolt head. We don't care much about that. All right. The shear just deals with the bolt directly. When we are dealing with stress, right, or bearing stress, when you see the word bearing, you need to deal with their area is now the interaction. Between the bolt and the plate. I'll get out of your way in just a second. By the way, those of you that are new to this room, there is a monitor there you can watch as well. All right, which Alex has a tendency to do, which I have to remember that's what she's doing. She's not just ignoring me. All right. Now the area is going to be, we'll call it what is, the cross-sectional area is what is touching. And I know I briefly discussed this and then y'all totally got lost. And then I took the picture in Mexico, which I think helped. So. All right. You're looking at what? You're looking at this area. When we're talking about the bearing stress, we are looking at the bolt and the thickness of the plate that it goes through, because we are now looking at a square. All right. So we have two parts of the square. Mine's a little big, but we have the diameter of the bolt, and then we're going to have our thickness. Now, when we have a double bolt, whether it's a shear or not, what did we do when it's doubled?
Divided.
Right, you have to, for lack of a better term, you're now going to distribute it. So if I have a plate running through here, oh, I made the plate green. I'll be consistent. The blue is my bolt. As you can tell, I did very well in art. You believe that? I have a bridge to some. Okay. So if I have this type of scenario where I have the bolt going through two plates, right? Now what's going to happen is we're going to have twice the area. So then we multiply the area by 2. All right. Meaning what? Meaning that that force is now being distributed among two plates. All right. Does that make sense? Because I one of the reasons why I pulled this problem is because I felt that we didn't have that this wasn't making sense the first time I presented it.
That's a good assumption.
Okay. Is it making a little bit better sense now, Kate?
Thank you.
You're welcome. Gibran, is it making any better sense now? Are you still there? I'm probably moving out of the camera frame when I did that.
It's been good.
Okay. All right. All right. So I'm going to send the rest of this home with you. In addition, 1.7, I wrote it.
So.
I'll make that a take-home quiz. What's up?
This is the take-home quiz?
No,
Oh.
that's group work. You're going to go home and finish it.
As a
Or,
group?
you know, the 3 of you will get together with a whiteboard and finish it, right? Not letting Tyler run the calculator. And then I wrote a proctored quiz for 1.7, but I'll go ahead and also send this home with you. All right, but you guys need to get caught up. Why are we falling behind? Why are we falling behind? Besides the fact we have to go to Bisbee.
Well, yeah, sorry.
No, don't apologize. Don't apologize. All right. All right, so hopefully this makes a little bit better sense. All right, how are you guys doing? So you did have the tools to solve the group work. I thinking Ellie, I worry that we're running in first, Ellie, 2 points. Point number A is when you send me a direct message, everyone sees it because of the way this room is. All right, so do some homework. Okay, that's my best response to that. Now, when you look at the homework, spend time with the homework from 1.6 on. All right, because I think that, you know, let's talk about maybe what you know and what you don't know. You already took a quiz on the 1.6 problems where you were dealing with what? The slope of the line, correct? modulus of elasticity, okay? Oh, you don't want the other online people to watch you. Okay, that's fine, you don't have to worry about it. All right, then we dealt with Hooke's law and Poisson's ratio. That was the smashing problems. All right, so that's 1.7. Then 1.8 was our shear, stress, and strain. All right, so now we're dealing with tau in those. And we're dealing with gamma instead. All right, and then, oh, I thought this was a 1.7 quiz. The other thing we talked about, so when we talk about your next exam, break it down into little stuff. You're gonna have to know your stress strain curve. You already took a quiz on that. Didn't go well. That surprised me. Right, and you're gonna have to know it for steel, stainless steel, and concrete. Okay, that's the wrong steel, isn't it? So, Brock, I'm dyslexic, didn't read till I was like 9, and I totally missed this day in school when we learned spelling. All right.
I'm also dyslexic.
Okay, good to know. So when I do a mistake like that, you'll be like, I totally get it. I know what
Yes.
the word is.
Always.
All right, perfect. Love it. Love it. All right. Hopefully you were diagnosed earlier than I was. Okay. Then what did we deal with? We then deal with, when we talk about stress, or no, axial stress, and we're gonna get into axial stress today, okay? Then we're dealing with sigma and we are dealing with epsilon, aren't we? All right, and you need to be able to do Hooke's law and Poisson's ratio. Is that right?
Yeah, yeah.
Okay. All right, we then talked about it when it was shear. Right? Shear stress comes in perpendicular. That's the key to it being a shear stress. Then we have tau, which is our stress, and then we have gamma, which is our strain. And one of the things we discussed, and I don't know how well this worked, one of the things we discussed is the strain is how much it will deform. Right, so that's our strain. Okay. We also, we had what? What with the axial stresses? What did we work with? Hooke's law. What did we do? We had what? We had E, the modulus. Which one is the tangential force? Don't really, we don't really have a tangential force. We have a force coming in. Young's modulus, yes, E is Young's modulus. Okay, it's a materials property. It has to be given to you when you do the problems. Shear stress, though, we don't have E. What do we have?
G.
Yes, you are thinking of fluids. We have G. Or you might be thinking about dynamics because we were dealing with normal and tangential things in dynamics. All right. Okay, the last thing we did that will be on your exam will then be allowable. So this is number 4, allowable loads. How well did we go over allowable loads?
Went over it.
Okay. N was our factor safety. right? Or safety factor, turn that around. And so we had what you end up with this equation. So sigma allowed is going to be sigma sub y over n. What is sigma sub y, people?
The yield.
It's gonna be where it starts to yield. Okay, and so in our stainless steel diagram, it's gonna be this point here where it's gonna start to yield, all right? We also had shear allowed. All right, so our shear allowed is then going to be tau u over our n, where n is our safety factor. Okay. Same thing. Oh, I'm sorry, it's tau y. I'm sorry. Okay, hang on. Tau y. All right. Now, this is what's different. If we have a ductile material, what does ductile mean? It can move a little bit, right? It's a little flexible. Maybe not super flexible, but it's a little flexible. If the material is brittle, right now, Google concrete. What does concrete look like? Here's the stress strain diagram for concrete. By the way, they voted, they wanted their project in here was to do some experiments with concrete, and we'll go over and break them. Because you guys have to, you guys don't, but you all have, you don't either. You guys have to take concrete.
Yeah.
Okay.
It's a mound, more or less.
Okay. Concrete, I thought it was.
Stress.
Mhm. If it's brittle, it's just gonna go boom. Yeah, concrete is a mound. All right, but so this isn't concrete. This is coffee cup. Right? Coffee cup, brittle, ceramic. Ceramics material, brittle material. All right. When we have a brittle material, things just come to a dead halt. If I drop my coffee cup, or I drop this glass bottle, for example, right, it's not going to deform, is it? It's just going to shatter. If I drop my water bottle, which I don't know if I brought that down from my office. I did actually. If I drop my water bottle, this is a metal, it's going to dent, correct? All right, so then we now are dealing with ultimate. It just stops. All right, and so if we have a brittle material, then our safety factor or are allowed okay, so if I tell you, you have the ultimate shear stress, if I give that to you, that's a bearing stress problem. Yeah, so I tell you, so number 7 of the sample exam, I guess we should just pass these out. I know those online aren't seeing it. I actually give those numbers to you. What is the other thing I promised to give to you? Reaction forces. I don't want to waste your time doing statics. We have statics to do statics. All right. Okay, so in the classroom, and I'll get it posted for you online, here is the sample exam for 2 weeks. Everyone but Simon. Simon's taking it next week.
You're taking
Austin.
it right now.
He's taking it right now. He's ready to go. Oh. All right,
Please no.
please don't.
Hear that?
Okay, and I will get those posted. Now, the folks flipping through the sheet, and I got a little carried away on what was supposed to be the take-home quiz. But, because I did it twice, you will notice I give you all the equations, right? If you look at the very back, do you see a long list of equations? You aren't expected to memorize equations in my class. Don't tell U of A that. I'm sure they want you to memorize equations, so shh. But my attitude is it's more important because your employer, when you go off and you work for Freeport McMoran, right? Or you work for, here's the take-home quiz, or you work for Sarco. Are they still a Sarco? Or are they Grupo Mexico?
They're just owned by Grupo Mexico.
They're owned by Grupo Mexico. Okay, but they're still called a Sarco. My husband was in mining. He was a mechanical engineer in mining for 13 years. So,
Did you like it?
what?
Did you like it?
He loved it. He loved it. You know, the only, and he loved it because he was the only mechanical on the plant. So he walks out of college and he's designing $2 million piping systems. Right? That's why he loved it. The only reason he left is he became the mine maintenance manager. And he said it was romper room, and he knew they were going belly up because Grupo Mexico popped them and then tried to spin the US Asarco off because they really only wanted the copper mines down in South America. And the US said you're not allowed to do that because all of the environmental liability is in the US. So a court said, no, you can't pull all the assets off, which is Peruvian copper, and leave all the smelter sites in the US. So, but I mean, he would come home. The only bad thing about mining, and it's not a bad thing, it's just an is thing. He came home one day and he said, I don't know if I'm going to get paid this week. And I'm sitting on the floor with 2 little babies. And I'm like, oh, really? So it's just something to remember, right? Right. When mining is booming, life is good. When mining is not booming, life gets a little interesting, right? So make sure you have your emergency funds set up. And he got a job offer in Colombia, but he didn't. He went down there and he came back and he said, we'd be living in a compound behind barbed wire. My children are growing up in prison.
No.
So that's when he left mining. And then he went to aerospace. And now he's a senior chief for aerospace, which means he sits in his office and says no. Or at least that's what I tell him that he does. He's like senior chiefs not in mining, but in the rest of the world. They have a tendency to, they're like executives. For lack of a better term. Okay. All right. So we're going to push ourselves ahead a little bit. All right. Your exam will be over chapter 1 with Boeing. No, he is with Honeywell. And he is a senior chief. All right. So I got 2 things going on here in the chat. Would there be an internship possibility for you? Do you have US citizen and can you get clearance? Oh, okay. Yeah, that might be a problem. That'll be a problem for him, but Honeywell does offer internships all over the world. He is a senior chief for power generation and electrical motors. Power generation, I'm sorry, and electrical engines. So all that product line answers to him. He's sort of like an executive in the sense he goes, no, you're not allowed to do that. Okay. All right. So second question, take home quiz 1.1.9. You can't find it. So it became group work. I emailed it to you. There's a take-home quiz 1-7. You're not seeing that one. I will upload that one after class today. All right. So we're gonna start in on this changes in length of axially loaded members and changes in length under non-uniform conditions. Okay, so we're gonna start in on this next week. Sure, you don't want to take the exam. No, I understand why. I just want to warn you. I think the hardest section in this class is next week, depending on how far we get today. All right. So you've been warned. All right. Okay. E versus G. All right. So we're going to start thinking about this like it's a spring. Okay. I could have brought the springs into play with. All right. So if you remember back to your physics class, those of you that took it at U of A, I'm sure it was extremely painful. All right, and I'm talking about physics 210.
Yeah.
Okay, so you're gonna have to email that to me, and we're gonna have to figure it out because you're not stateside, right, Musan? You're not in Arizona, correct? Oh, you are in Arizona. Okay, come get a piece of paper. Oh, you're in Tempe. All right, I'll email you. You'll have to email me and I'll get you the piece of paper. Okay, so back when you learned springs, right? What did you do is you learned that your force in the spring was equal to Kx, correct? And what was X? K was a spring constant.
X was displacement.
And X was the displacement. All right. If you look at the diagram with the force is an axial force, isn't it? The spring is being pulled along an axial direction. What we are going to do is we are going to use this similarly, but we're going to look now at, we'll just look at rods. I think later on in the class we move into some more complicated stuff. All right, and we're going to do it with analogy of Hooke's law. So that is our force is no longer a force because your author likes to call it. This is the class where the author makes all forces P, right? So P is then going to be K delta. All right. Yes, direct length minus the initial length. But I get over 50 emails a day, so feel free to email me multiple times. All right, because I'm also under a lot of stress. So my brain is not functioning as well as it should. And I didn't get up to go do my little old lady class at the Y this morning because I hit snooze and woke up and it was 6:30 and went, whoa, screwed that up. So P is my force. Now, the spring constant is a material constant, correct? So is K. K is known as my linear elasticity. All right. We will also sort of think about it as stiffness. Delta is then going to be the change in length. Okay, so chapter 1 is all about our shear and our normal stresses and then how things are reacting to those, right? Now, what we're gonna do in chapter 2 is we're gonna start deforming stuff, which is what makes this class fun. Oopsie, hang on, right? We're gonna deform it axially, meaning we're gonna pull it. We're also gonna have to do that under non-uniform conditions, and then we're gonna have to do it under indeterminate statistical conditions, which is where this class, in my opinion, gets a little more challenging. Okay, so we got our equations down. Oh, by the way, K is stiffness. Oh, what am I doing? K is stiffness. The other thing that you might be given is F. I'll make it a little fancy F, which means flexibility.
That'll be given,
What?
that'll be given.
It has to be given because
It's like
it's a materials property, or you can look it up. So those of you that have the hardcover book, in the back, there are all those appendix and tables, and then that, and it'll be listed there as well. So if you're doing your homework and it says we have SAE 30, you would look it up in the back, okay? And it's a materials property in the back of the book. If you are taking an exam, I have to give it to you, right? Or I start doing what I did in thermo and I just start giving them all these tables and charts, and then they end up with these 20-page exams, and then they come into thermo and they sit down and they freak out. And I'm like, it's only 4 questions. The rest of it is steam tables, because mechanical engineers, man, they worry about those steam tables. So our stiffness and our flexibility are then going to be inverse of each other. All right, so our our stiffness, which is kappa, the flexibility is then going to be 1 over that. All right. Someone logged into fluids. Okay. How are we doing? Melody, how are we doing? Maybe she's not online anymore. All right. So now we're going to start talking about prismatic bars and what the difference between these bars are. I've got a page on axial loading. Did I just get this in the wrong order? Okay, let's go ahead and talk about axial loading. Right, when something is loaded, we're putting it under a particular stress. All right, the thing is, when we're discussing it as being axial, right, then it's going to be parallel to the longitudinal axis. Okay, so what does that mean? If we have a bar, okay, if it's axially loaded, it can be axially loaded 2 ways. One is if it looks like this, then it's going to be in tension, but the force is along the long part of the bar. All right, we've already discussed this in theory. This will be a different set of a series of equations, but if I'm bringing force in like this, that's what type of force?
Shear.
That's our shear force. Okay. All right. So tension is going to pull it. Compression would be the other way it's going to happen. Compression is going to do what? It's going to push it in, right? So if we have compression, it's going to push it in. We are going to treat these as single forces. That is really not the case. In fact, if you think about it, right? Really, what's going on here? What do we have? If we are dealing with the axial load, we are having a field of forces, aren't we? All right, but we have to crawl before we can walk. All right, so let's talk then about how we're going to work this and what's it going to do. And we're going to start with what is called the prismatic bars. All right, was that a little quick? Do I need to back up, Tyler? Tyler says we're doing okay. I'm getting cold though, but Tyler says we're doing okay. It's after 5 o'clock. You guys write this slide down. I'm going to unlock the door so we don't have to prop it open and set off alarms. Door is now unlocked. Okay, so prismatic bars are our perfect condition. So when we have something that's prismatic, they might be looking for calculus for fluids. So give that back to me at the end of class and let me go ahead and rave those prerequisites as well. All right, I'm sorry. Those of you who haven't had class with me before, my ADHD is strong and overwhelming, and so I get these squirrel moments. That I don't have a filter. So it is, so first off, they're gonna be straight. No bends, no curves, no funny stuff. They are also going to be uniform. What we're going to realize when we move out of chapter 2 is not everything is uniform. In fact, I think in 2.5 we start getting mismatches. All right. Or maybe sooner. Oh, it's sooner. It's actually in 2.3 we'll start getting mismatches. All right, meaning what? We have the same material. All right, we have constant density. All right, and we have a constant cross-sectional area. All right. Okay, so we have, if we have this going on, all right, meaning we have an ideal perfect bar, right, Alex? All right, then there's an equation we can use for it. And that equation is our change in length or delta is then going to be PL over EA. And let me tell you what all of these mean. Right? Delta is the change in length. All right, P, your author likes to use P for force. So that's the force involved. L is our starting length. So this is the length with no force. Okay, we don't have any force pulling on it or anything else going on. E, you guys already know. What is E? E is Young's modulus.
Just to be clear, Young's modulus and the last, or modulus of elasticity is not the same thing? Or
No, it
the same
is.
thing?
So is this all, are we all talking about these forces in tension right now?
Doesn't matter.
Okay, so it's not
Doesn't
gonna
matter.
change,
As long as the
like, the
prismatic
last
bar
section.
is all.
As long as it's a prismatic bar, this is gonna work. A is area. Now, what's gonna change? Well, I know these are for tension. You got your book open, that always makes me nervous. All right, I believe we get a negative delta.
Okay.
Don't quote me on that.
That's impression. That would make sense.
Yeah, when it's in compression. Right. Yeah. All right, we're doing okay. I'm getting some side chatter from the classroom. So my guess is you guys need a break. Is that correct? All right, let's take a little break. We'll discuss how the cross-sectional area changes, and then we can do a problem.
Could you move up in the slide a little bit?
Sure, be happy to. Where do you need me to be?
Just a little lower, but about there. Thank you.
All right.
You said,
It's great. What did you say?
said we'll do a pass for it.
ENG 219. Oh, let me make sure I match this up. 31 90 125 66. The class is cross listed, taken at U of A.
Then for us, for our fluids exam, what's your recommendation?
So once you're in the class,
I can send it to you. I'll do it.
she can send it to you. The other thing is, all of these, because I've got virtual people, all of these lectures are recorded. So once you're in the class, you can then you can watch the lectures. Because everything is recorded and uploaded to YouTube.
Awesome.
Okay?
Thank you very much.
Yeah.
Honestly, just gonna, instead of doing what I did last time, I'm gonna just give you my D2L login.
You can
Is
give
that
them the what?
my login, because I made a whole PDF with everything, but it look, took a while.
Don't do that.
Well, I
The
did it
other
so they
thing is,
have
once
it.
you're in, email me and I'll open up the quizzes they've already taken.
Okay.
Can I ask about a quiz in this class? So it was the one from last class, but I took it on Sunday online.
Yeah.
And on the second question, it says there's a reaction force at point C, but
Yeah.
there's no point C listed. So,
Oh, I meant with the concrete part.
okay, then I probably messed it up.
Well, that's okay. Quizzes
So-
are learning experiences.
Yeah. Yeah, Amelia and I were talking about that, but I assumed, I still think I did it wrong, but it's fine.
So I'm gonna hit the restroom. To answer your question, Ellie, 2.1 and 2.2, the unit on energy and work, that's the wrong set of slides. Those slides belong to thermodynamics. They don't belong to you guys. Here. If you want, you can take a picture of
Be
my
great.
solutions.
I've been flip-flopping everything too already, sorry. Cause
That's okay.
everything's opposite in the other class, so it's been something.
Okay, so we need to go over question 2 on that quiz. I'm gonna take that back from you.
That'd be great.
I'd like to let them get a chance to take it, but we'll go over it.
Yeah, I just didn't convert something and then I totally did it. For what I guessed, I feel pretty good, but
Okay,
yeah, no, yeah, it's just wrong, but that's fine.
okay.
Thank
But
you.
the key is your stress is gonna be your force divided by area.
Yeah, I've been doing that one, thankfully. I just didn't know where to place that reaction force, so I had a negative cosine and then
Oh, okay.
I had a positive force, so. That's no biggie. I'm not too upset about it for not being sure about it. That first question was great though. I've been doing that in structural, or not structural, geometric, so.
Oh, have you?
Yeah, we've already, like a lot of what we're doing today, I've seen thankfully.
Oh, okay, so I go faster?
I
No.
no,
Brain.
I saw it once.
Then my overthinking will work. There we go.
All right, so. We left, I'll give you guys one more minute, so it's even, 5:20. Take 30 seconds.
I'll have to take and wind it down.
That was the issue.
Help you out, don't you worry. You want a 24 pack?
30 rapid.
Guys.
All right, folks, let's go back to work. One of the, I don't wanna say biggest, but concerns that you will need to address as you do these problems is this cross-sectional area. All right, and I've seen students fight this in the past. So what happens is you will have solid cross sections, all right? When we have a solid cross section, if it's a circle, then we're back to pi r squared. If it's a square, its length, oh, I guess I'm doing that backwards. All right, it's gonna be length times width. If it's hollow, life gets a little more, we have to be careful when it's hollow, okay? And we did this when we were shoving the steel into the plastic, or was it the other way around?
Plastic.
It was plastic and it was a plastic liner. All right, so you're going to have your outside area and then you're gonna have your inside area. So your total area, you're gonna have to subtract it. Your outside minus your area on the inside. All right, okay, beams. Beams are a little wacky when it comes to cross-sectional area. All right, so what you're gonna wanna do with beams, and we're a little ways away from dealing with the beams for this class. I don't, do they let you look them up? You guys don't. Right. I will either have to give it to you, or you can look it up. And it depends on a lot of stuff. Not only, and the problem is this little area here, which is called webbing. Okay, no beam is just 3 rectangles. Okay, it can't be, it's not gonna happen. But you get this area in here, that's an over exaggeration, but you get that over area in there which is curved, and that curve is called the webbing of the beam. And that's gonna change what the cross-sectional area is. All right, I've given Brock a headache. All right, so okay, mining people typically don't have to worry much about this. But as engineers, you will, and I believe you have to take a beam class, is that correct?
Suckers.
I mean, we gotta take a class for.
You have to take class for everything. Well, not for everything, because nothing moves in your world, so you don't have to take like dynamics.
True fluids move.
Fluids move, all right. I guess fluids move. Oh, there's the axial loading slide. Gotta love it. All right, we talked about this. Stiffness is K, flexibility is F. Okay, so let's go ahead then and talk about cables. And the reason why is, once again, we are going to have to, we're gonna probably be looking these up. All right, and we're gonna do a problem where we're gonna have to look it up. So that's why I pulled this. Okay, so when we're looking at our steel cables, all right, they are not a prismatic solid from that aspect, are they? There are a whole bunch of prismatic solids that are woven together. All right, and so if we're dealing with a steel cable, this is in your book. Those of you that have your book with you, on page 123. All right, and we're going to do a problem with steel cables. So once again, all right, we're going to treat it like it's a prismatic bar from the equation standpoint that we're going to use, but reality is you're going to have to, based on the type of steel cable you have, we're going to have to look it up here to see what's going on. All right, by the way, ultimate load is going to be what? Or it's going to be the yield. It's going to be where it breaks. Can anyone else hear me? Oh, okay. So, Musin, you might have to log out and log back in again. All right. And by the way, if you buy this steel cable, you're not allowed to return it, but you can get a bulk discount. All right. Anyway, and it's not eligible for free shipping either.
Oh.
I know. Tell me about it. All right. So let's look at an example. This came right out of your book. So go ahead, take a screenshot, write it down. Let me know when we're good to go, and I'll scroll down, and then we'll keep going on this. And we will do this problem.
In reality, do we treat everything like the prismatic bar, but that area
Absolutely
gets
not.
changed? Okay.
Absolutely not. So, but so Ellie says she's good. Give me a 7 in the chat. Reality is, no, you can't treat them as if it's a prismatic bar. And one of the things that's going to happen is we will get into what they call non-uniform conditions, right? Which is when we have stuff behaving because we've got a change in diameter or because we have a change in material. So we will get into those equations as well.
Okay.
And then we'll also deal with it when we're dealing with thermal stresses, and then impact loading is also going to be a little different, but this is a good place to start. All right, so chat looks good. I've got some folks in class writing. By the way, you guys can take a picture of this if you want. You can also, they've got their books open, so it is 2.2-4 in your book as.
It's page 227.
All right, so it's page 227 in the book is where the problem is. I'm gonna go ahead and scroll down. And so this is the picture of what we are looking for. So mining engineers, you probably won't have to order these, or you'll have a part specific to order them, but you can also think about these cables. A lot of these cables are on your drag lines. All right, and so this, if you had to calculate your drag line cable, this would be something you might want to use. In addition, right, sometimes cables are used in tailings. So that's the other time when you have to worry about how, and that then brings this class together with Alex's other class, which is what, geomechanical. So you would use the geomechanical to figure out your forces, and then this tells you how that cable is going to respond to it. Usually though, those are going to see shear stresses. So a steel cable has a nominal diameter of 25 millimeters, and it sends you to the table that was just on the board. Is used in a construction yard to lift a bridge section weighing 38 kilonewtons as shown in the figure. So there it is. All right. The cable has an effective modulus of elasticity of 140 gigapascals. And when you guys were writing this down, Tyler mentioned, or Cade, that, well, is it always going to be uniform? The answer is no. The other thing is this says it's effective, because the other thing that will happen is this does change. All right. If you're putting this under a lot of stress, it will change with time. The cable's 14 meters long. How much will it stretch? So if I want to know how much it will stretch, what am I looking for? We're looking for the delta. All right. So that is code for, we are looking for the delta, and then if it's rated for a maximum load, we're then back to our safety factor. Okay, so we are given some information here. We are told it has a diameter of 25 millimeters. So if we go back to this, right, a nominal diameter of 25 millimeters, that's going to put me in this row here, isn't it? All right. The first number is in inches. The second number is in millimeters. All right. Yes, Melody, we're going to look for that delta. All right. So we then have our weight, but what we are after is the effective area. So the effective area, the cross-sectional area of this is then going to be 304. It's coming off the table for this problem, right? Because we have a steel cable and those are interwound. All right, the other thing, oh no, we're lifting a bridge of 38 kilonewtons. Okay, so let's go ahead and start in on this problem. By the way, the bridge section is already given to us in newtons, so that's very convenient. All right, and we are also given E, so I guess we are good to go. This, let's break this down. What is this 38 kilonewtons? It's my P, isn't it? All right. E is given to us as E. This is my what? That is my initial L. Okay, that is the length before we put any load on it. All right, so at this point, now that we have torn that problem apart and diagnosed it, what do we know? Well, we know everything we need. We know the area is 304 millimeters squared, and we used calculus to get that, didn't we?
Correct.
No, we read it off the table. All right.
Somebody did calculus to get.
To be honest, someone probably just chopped them up and measured it. Okay. All right. The weight is going to be 38 kilonewtons. Because even though we would love to think that our lives are ruled by calculus, not really. Okay, E is 140. Sorry about that.
Is 38 kilonewtons
That's your
P
P,
in
right?
this case?
Yes. Yeah, that's your P. I wrote it as weight. I need this to go away. I hit something. All right. So it's written as weight, but it's gonna be P for us. So that is the force. Now, if the weight was given to us in kilograms, what would we have to do?
Gravity.
We'd have to multiply it by gravity. Okay, and then what are we gonna have? We're gonna have the length is then equal to 14 meters. Okay, now. That's in millimeters squared. We're gonna have to deal. No, we're gonna leave it alone. This is in gigapascals. Okay, so let's go ahead and look to calculate our delta. That is PL over E times the area. Newtons is going to be kilograms meter per second squared, correct? All right. Okay, I think it's going to all work out. The author strictly puts it in. I'm worrying about units because that's what I do. All right, so he directly plugs it in. So the length is 14. I'm going to lose the meter in that one. This is gigapascals. And then we're going to have 304 millimeters squared. We're going to have, let's deal with that. I think that's what we're going to happen. Plug this in for me. I'm seeing a unit problem and it's giving me anxiety. All right. Do me a favor and plug this in and see what do you get when you plug the numbers in as is?
Yeah.
What do you end up with?
1/80.
Okay, so we're gonna have to deal with that. You end up with 1/80, which is
0.0125.
0.0125. All right. And you put in the 304?
Yeah.
This then has to be in meters. Oh, there's the gigapascals. That's where it's gonna go away. Okay. All right, I'm feeling better. So then that would be then 12.5 millimeters. We're gonna, because, okay, so we should convert that millimeters to meters, shouldn't we, to do the calculation? But we have the gigapascals. So those thousands are gonna cancel themselves out. Brock doesn't believe me.
Yes.
He's lying.
No.
But
I have to convert everything first.
you
Like,
what?
I have to convert everything first. I can't. do
Okay,
this funny
that's fine.
business.
You can convert. You ended up with 0.0125 meters when you converted?
I didn't, but
Oh, you didn't run it. All right, I know, I'm always telling the class to run numbers, and I'm like, someone from the administration is gonna watch one of these videos someday and go, she's talking about gambling. All right. Now, we now need to figure out our safety factor, which is N. So our safety factor is always our ultimate, right? How much can it handle over our max? All right, our max on this one is, oh, sorry, wrong screen. Our max on this one, it's rated for a maximum load of 70 kilonewtons. All right. So we know our max load, P max equals 70 kilonewtons. How do we know what P ultimate is then?
You look it up on the table.
You look it up on the table. All right. I'm starting to feel like, so that's then going to be 406 kilonewtons here because that's the ultimate load that it can handle. All right. Yeah. So it's the joke, and when I teach statics, the joke is free body diagram. Whenever I ask a question, they always tell me free body diagram because I beat them up over it. So in here, it's go look it up on the table. All right. So we will pull the 406. So now we can calculate our safety factor involved in this. What is it?
5.8 safety.
5.8. So we have a safety factor of 5.8. That's a really high safety factor.
That's good, right?
Yeah, it is.
Overkill.
What is the trade-off though?
Expensive.
It's gonna be more expensive, right? Right, so you might want to go one, sorry, I'm thinking. Or, well, that's a little overkill, but if you had a max, if you said your max was 100, the other thing you could do is we were given this max load based on the cable rating. You could also then understand that if you're only worried about a safety factor of 2, right, then you could change what that max load is gonna be. The problem with this is what? We're taking a little side trip. What would be the problem if that cable broke?
Kill somebody.
You're gonna kill somebody.
Tell them not to stand under.
No, it's
So
not.
true.
I'm not worried about, I don't care. If someone's stupid enough to be standing here, they can die,
The
Right.
cable would-
right?
Cable.
If the cable is gonna do what? When it breaks, right, this will fall down. What's the cable gonna do?
Retract.
It's gonna retract, it's gonna smash through the cap. All right, I would be more worried about that than some idiot standing underneath it. Because they shouldn't be standing underneath it anyway. But don't worry, they're standing underneath it, but OSHA's okay with it because you're wearing a hard hat.
They got a tagline too.
You'll be good.
Yeah, it'd be all good. They've got a
Dr.
hard
Mickey?
hat on.
Dr.
All
Minky,
good. Yeah.
in your experience, like what kind of safety factor do you typically see?
Typically your safety factors are like 1.6 to 2-ish. Just depends on what industry you're in. If you're dealing with military, they're gonna have a much higher safety factor than if you're dealing with commercial product lines. Okay, but as I
Got
said,
it.
you've got that cost variable in there. So
Right.
a lot of companies, this is a textbook problem, but a lot of the companies wanna run a lot, they wanna run a lot closer. Okay, so they'll want a safety factor. Aerospace typically runs a safety factor of 1.6. For example, what is mining safety factor? 0.2?
Is safety
Or-
factor unitless?
Hmm?
Or like, there's different, like a big slope or like
Yeah,
usually around 1.
round 1, okay? So, yes, safety factors are unitless. So a Pascal is a Newton per meter squared. See, that's what we were talking about. So we got a gigapascal, which is gonna multiply by 1,000, and then we have millimeters squared, which is gonna be 100,000. But I will leave that up to you to go through.
Sorry.
What?
Millimeters is by a million. Since it's 1,000 by 1,000 equals a square meter.
Right,
So not 100,000.
but gigapascal's more than 1,000, isn't it? Anyway, we're not gonna fight the units. Feel free to fight them on your spare time, Ellie. All right, that's so, how are we feeling about that when we're dealing with axial deformation?
That was good. They gave us everything.
We're feeling okay with it. All right,
They did give us everything.
they will, and they will give you everything anyway, right? Because you want to see how much it will deform and then possibly calculate out a safety factor. All right, so let's get into when things get weird. Prismatic is our perfect world. It's our textbook world. Now we're going to get into non-uniform conditions. And that's when things are going to get a little more exciting. Okay. So let's talk about what's going on. We're still talking about our axial loads at this point, and we're talking about pulling and stretching things. All right. So prismatic, and this is one of the bad things about this class, is the fact that you get a lot of material at once, but it's only 1 day a week. So it's a trade-off. As I was mentioning to Brock, you know, if you start spacing out, you can always go back and watch the videos, correct? Your brain is in overload. You can always go back and watch the videos. I also post all of these notes online as well. All right, so you have no excuse not to be amazing with this. If it's prismatic, you can also do it as segments. In fact, that might be a good idea. Let's do one where we can do it in segments. All right. Or well, we can split the prismatic into segments. Let me see if I have one in here where we're using, oh, I do already. Okay. Never mind.
That would be using the prismatic elongation for 3 or however many sections.
Right, but we're still gonna assume that our density is constant and our material is constant. So when we talk about prismatic segments, and we'll do a couple of these problems, all right, we might have a bar that looks like this, and then we've got a secondary bar that's a different size. What we're gonna do is we're gonna do exactly what we did. We're just gonna add them up. So when we have prismatic segments, our delta is then going to be, I lost the equation. It's gonna be then, we're gonna add up these for each one. So we would then have force, we would have, oh, it's length on the top, isn't it? Over E and area. Okay, and I guess we could also change materials and have slightly different E's in there as well. So we could have steel and copper that is welded together. All right, and we're gonna spend time working, we are gonna do some of these prismatic segment problems. All right, the next one is typically called an intermediate problem or an intermediate beam. All right, when we are dealing with this one, we are going to be dealing with varying loads. So we in each segment, so in varying loads in the segment. The prismatic, we are assuming that the first section might have a load on it, the second section might have a different load on it, but it's the same inside. All right. Whereas when we have what's called an intermediate, then you might go, okay, well, I'm going to have a big load here, but then I'm going to have a little load there. So the load is varying based on the length of the beam. All right, how are we going to deal with that? Going to have to do an integral of our loads, and typically that integral is then over a change of length. Okay, reality, when you guys are actually in the industry, you will probably just set up, we as an education in the US, we do a very, very poor job of educating you with Riemann sums. But you're basically going to do Riemann sums the rest of your life. Yes? Oh, I thought I heard somebody. You're going to do Riemann sums the rest of your life. In fact, I keep saying this, and I don't know, maybe it'll turn up into existence. If they made me queen of math, I would get rid of Calc 2, not get rid of it. All you need is integration by parts, separation of variables, and use substitution. If you can do those three, you're good for the rest of your mathematical career. All right. But you really should be able to do everything in Calc 1 and all integration techniques in an Excel file. Okay, because that's reality. Reality is to be able to go ahead. The third one is when we get really ugly, and that's when we're gonna have, and I don't have a name for it, varying loads and varying dimensions. So not only is the load gonna be changing, you know, if we have something that then looks like this, then our cross-sectional area, it will be changing as well. All right, so once again, that has to turn into an integration. All right, but we're gonna focus on what's gonna happen with these prismatic segments. Right, and that's what we're gonna work on with these non-uniform conditions. Same thing when we do thermals mismatches. All right, so let's go ahead and dive into this. Well, okay, let me back up real quick. I have a beam, I cut said beam. When I cut the beam, what are my internal forces on that beam?
Axial shear and bending.
All right, they're gonna be axial, they're gonna be shear, and they're gonna be bending moment, right? All right, and so ultimately, we are gonna have to bring those internal forces into what's going on based on where this is occurring. So if I have something, and let's say I take a measurement here, or a calculation here, and a calculation there, right? Those would then become our internal forces. So we're going to start looking at these prismatic sections. And we're going to look at them when we have this is the intermediate axial load. Let's back up and do a prismatic section problem. Okay, so let's say we have a steel rod and we're going to hook it into a wall. And we're just looking at the side view. All right. Okay, and we're gonna have some forces in here. So to start with, I'm gonna go ahead and just give you those forces, and then we'll work on splitting this up. Okay. So we're gonna have a force, if this is at A, and this here, we'll call this B. All right, so we'll make this 12 inches. Right, my force at B is then, we'll go ahead and say it's going to be 75. The notes I have are in kips. We then move out another 12 inches. This interface has a different force on it, and that's going to then be 45 kips. So what's happening is I'm looking at these as, we're going to break this into individual prismatic bars. Over here, then, so we'll label this C and this D. D is seeing, D will make it 16 inches long. D is then going to see 30 kips. So we went in, we cut the bar up, we measured the force happening, or we calculated out those forces. The area of the blue part is going to be 0.9, cross-sectional area 0.9 inches squared, and then the area of the green 0.9 inches squared. All right. And we want to find the total deformation. Okay, this one we're given all the information. We don't get to look anything up in a table. So when you have this written down, let me know, and then let's walk our way through how we're going to work through this. Except Kate is yawning, so now I am yawning.
Sorry.
That's okay.
Sorry.
So what would we use for the modulus?
Oh, modulus is going to be constant. And we need to know that, don't we?
Yeah.
So our modulus on this is going to be 29 times 10 to the 6 psi. What'd you say? All right. So give me a 7 in the chat when you guys are good to go. And we're going to tear this apart and solve it.
Oh, just gotta break.
Mhm.
Gotcha.
So I don't know if you guys could hear over the room mic, Kate and Tyler were talking about it. They said, this isn't that bad. We're just going to break it up and then sum it together.
That's what we gotta do. It's the basics. It's just the basics.
You guys. It's just the basics. All right, we're also going to assume this all adds up to be 0. Now, breaking it up is going to be a little interesting. So I'm looking for 7s in the chat. Let me know how we're doing in class. Alex, you want to take a picture of this or?
I'll just get it from the slides later, actually.
Okay, you'll get it from the slide later. All right. So we are given, right? The lads said what? The lads said, well, we just need to break it up. But it's going to be just a little bit more complicated than that. I understand we know where these forces are, correct? But when we actually do the physical breakup, well, one of them is going to be a little more straightforward than the other. Let's start on the green end. The green end is going to be its own section. Okay, and let's talk about what the green end is. The green end is seeing. So I'm just going to pull the green part out. Okay. So if we look at the green part, that's what we're going to start with. And then we're going to have to get a little bit more creative. All right, so we'll call this our section number 1. We know that this has 30 kips here. Okay, so that means that it also has to see, right? It's going to be in tension by 30 kips. We know the area of this first section is what I say 0.3 inches squared. We know its length is 16 inches long. Right, and what else do we know about it? Oh, we know the modulus of elasticity stays the same for all of them. All right, it's in tension. Since it's in tension, is it going to be positive or is it going to be negative? It's going to be positive. All right, so let's calculate delta for segment 1. All right, so, by the way, if we convert kips to pounds, what do we have to do? Multiply by 1,000. All right, so what are we gonna end up with? We're gonna end up with 30 times 1,000. That's gonna be my force. Okay, we are then going to we're gonna have to multiply that by my length, and my length on this one is 16 inches. We're then gonna divide by the area, 0.3 inches squared. All right, and then we're gonna multiply by E, which is 29 times 10 to the 6, and that's in pounds per inch. So that units are all good. Go ahead and run the numbers for me on this. What do we end up with? This is a 10 to the 6, by the way. What'd you guys get?
I don't
Not
trust
you.
myself.
0.05.
Okay, I have a final answer, but that's fine.
I got the same.
Oh,
Yeah, God, it's a miracle.
What'd you guys get? Point what?
0.552.
Is it 1, 0, or 2?
I got 1, 0.
Oh,
I got 5.5 times 10 to the negative second.
All right,
So, before we continue. When you drew the CE section and the green section, you had the right, it's going by 30 kips, right?
right.
And so, once you cut it away, you didn't include the 45 kips compressing the blue section.
We're gonna have to put that as a separate section because of that 45.
So,
So my cutaway, I mean, I labeled this as 16, but you can think of it this way, I'm cutting this right before we see that 45 compression kips. Because that's then going to give us our next section, so to speak. All right, because we are gonna have to, and this is what I was mentioning, now, when we go to cut this, we have this compression section going on here, don't we? So we're gonna wanna cut this basically there.
in the middle, between B and C.
Yeah. I cut it in the middle. Well, no, I didn't, hang on. 30 minus 45 and negative 15. Let's cut it right before, oh, great. Let's cut it right before it sees the 75. Okay. All right, so our second section. We're now gonna deal with that 45, but we can't forget the 30 that's hanging on to the other side, correct? We did the green set, we all agree we did the green one.
Yeah.
Green one's good. We're now gonna deal with the red segment, all right? I'm gonna draw it this way because we need to talk about what's happening with the forces. I know I have a force here of 45 kips, but I can't ignore this part here where this is being pulled at 30 kips. So I have a compression and a tension, right? We are going to have to then, to get our force, right, what we're gonna have to do, we'll call this P2. What we're gonna have to do then is we're gonna have 30 minus the 45, which is gonna give me then negative 15 kips. All right, I can't ignore that 30 is still acting on that segment, isn't it? We are only gonna calculate our delta on this segment here. We just have to take into account that we've got those 30 kips hanging out there. Go ahead.
What's the rationale for doing the 30 minus the 45 as opposed to 45 minus 30? Like, what's the sign?
So 30 is intention,
So it's positive.
so it's gonna be positive.
Okay, so you sum them in the way that they are. As
Right,
pressure
if their
tension.
intention, it's positive. Like what we're gonna then deal with for the next section is we've got that 75, right? That's now gonna be intention, but we've got 45 compression coming in.
Okay. Okay.
All right. Oh, and then we gotta deal with the 30 as well, because we're building this up, so to speak. So let's get our second segment. Are we, online people, are you okay with the negative 15 kips? Because there was a question in the classroom on where that came from. Amelia's all right. It is directional, Elisandra, but it's the happy beam versus the sad beam, compression versus tension. Your bronze says explain. So if I have something, we agree, if I do this, it's intention, correct? In this class, and I'm sure geomechanics is backwards because you guys seem to be doing everything backwards in geomechanics. All right, if it's intention, then we're gonna have a positive, the force is gonna be recorded as positive. Right? Amelia, are you in that?
She is.
Okay, so this class is just gonna be backwards. If we're in compression, actually, I think this class is right.
No, yours is right, don't worry.
Okay. Except I can't spell compression. I wanna put an H in there.
No, there's just two S's, but.
Oh, there's two S's, thank you. Brock didn't miss that day at school. All right, if it's in compression, we're gonna record it as a negative force. Why are we doing it this way? If we're in compression, delta is gonna be negative because it's going to shrink. All right, so that was the rationale for the engineering world to set it up this way. Because if you think about it, if tension, your P is positive, you're gonna make it longer, aren't you? So your delta is then going to be positive because it's gaining length. If we're in compression, we're smashing it, it's gonna get shorter, correct? So compression, P, your P is gonna be negative, and the delta is gonna be negative. I have a meeting coming up on U of A for U of A department heads. Who's teaching your class?
My geomech?
New mechanical?
Ed Wellman.
Ed Wellman?
Yeah.
Okay.
The only reason they do it like that probably is because the math looks really gross, so it keeps everything healthy. That's what he.
You can handle gross math.
We cut the area in half then?
What'd you say? No, because it's cross-sectional area.
Sorry.
Oh, I'm sorry. I didn't mean to yell at you. I'm just very loud.
He's kidding. He's got thick skin.
No, he just likes to give me grief.
Yeah.
I realize that. I realize that. And I've had to warn him off. I've had to say, I'm really sensitive today. Shut up. All right. So we end up then, so Gibran, we've got negative 45 because that's in compression. And then we're adding 30 because 30 is in tension. This makes sense because 45 is going to the negative x-axis. 30 is going to the positive x-axis. And it makes our delta correct. That's why the geomechanical guys are backwards. What?
So is what's the reason why we don't do the 75?
We
minus-
will in a moment, we're not there yet, because we cut it before it hit the 75. Now, you're right, when we look at that final segment, we're gonna have to take all those forces into consideration. The 75, the 15, or the 30, and the 45.
Thank
All
you.
right,
So.
No, go ahead.
I'll save it for later, because I was about to ask you about that section, next section.
all right, so let's do our calculation on this particular section. Right? What's gonna happen on this section? Our delta is then going to be what? So we have to multiply that by 1,000 because it's in kips. Right? We're then gonna multiply it by 12. So Simon was getting ready to say, crazy lady, why are we not multiplying it by 28? Because we're only interested in that section there. But that section still sees that 30 intention. Okay. All right. So times 12, and then we're going to have what? On the bottom, we're going to have 29 times 10 to the 6th. I'm writing it backwards this time, 0.9. And that is my area that was given, my cross-sectional area that was given to me in that section. Right. I've got Alex is running numbers for me. No, she's not.
No, I am, I just don't know if it's right, but
What'd you get?
I got negative 0.0068.
That's good for me.
Alright.
I like it.
Okay. Now, I know we're tired. Does it make sense that it's negative? I've had tea, so I'm in good shape. Does it make sense? And I slept through it working out this morning. Does it make sense that it's negative?
Yeah,
Yeah,
the
more
BC section
compression.
is
Yeah.
press.
Tension.
It's compressing, so it's going to be negative. This is why this class actually makes sense. All right. And I know you guys are smart enough to handle the math. Let's look at section 3. What was that?
You're just making Kate blush,
Oh.
you can do the math.
He can do the math. All right, let's look at section 3. The class that I get really grouchy about is actually thermo, because they really don't think the students can do the math. And I'm like, just integrate it. Don't look at the crazy equations. What is this section seeing? So if you think about it, where am I cutting it? This time we'll make it black. We're gonna go ahead, we're gonna cut it here and figure out what it's seeing. Okay, so if I cut it there, what forces am I gonna see? I'm gonna see 75 heading that way. I drew that really small. Oh, and we'll even make it black since that's pretty. That's probably too big. Done. All right. So if I'm at this point right here where I cut it, what am I seeing? I'm seeing 75 heading off that direction, aren't I? I am seeing 45 heading in this direction. I'm then seeing 30 heading out that way.
So could you also just you came up with, say, I think you marked it as like P2.
Yeah,
Could you use P2, which, because it's a combination of both 45 and 30 for this?
I think so. Let's check it. All right, we'll call it P3. Because that's going to be what? 75 positive or negative?
Positive.
It's intention going towards the positive x-axis. 45 is going to be negative. Yeah. So yeah, you could have done it that way. 30 is positive. All right. So we're going to end up then with 60 kips for that, aren't we? All right. So our delta for this one is then going to be 60 times 1,000 times 12. All right, it's 12 because this section's 12 and that section's 12. We all okay with that? All right. You know, Robbie, I like you in class and you give me thumbs up, you give me feedback. You give me positive reinforcement.
That's awesome.
I need more of that in my life. All right. 0.09. All right. So you plug this into the calculator. Ellie has a number up there, but I don't know what it belongs to. Ellie, does it belong to this one? Okay. So this ends up being 0.0276. Once again, we are in inches. All right, at this point, we need to add them up. Because now we're going to sum up all of these parts, and then we have to talk about what's happening at the wall. All right, so we have 0.0052 point, there's only 1 0 there, right?
Yeah.
We are then going to subtract due to my compressive force. We are then going to add 0.0276. So we pull all of this together, and what do we end up with? No, it's not going to be 0. It's going to deform. Not sure why we're packing up. We're just tired.
I put my calculator away because I'm not gonna.
You're not gonna be using it. All right, 0.0765. I love that answer. Okay, so 0.0765 inches. Okay, a lot of times though, you will see it reported like this. Inches. Oh, I have 75.9. Anyone come up with 75.9?
I didn't,
Oh, and you did too?
no problem.
We'll have to put Ellie on the do not pay attention to list. All right, I would take either answer. All right, so by the way, this is going to become important later. I know you don't believe me. Hang in there. Okay, I will let you out early because we're supposed to technically take 2 breaks, but I will let you out early. There is a wall here. We all agree? Is it going to be able to expand into the wall? Okay, so actually, it's going to become 0 at the wall. Delta is going to equal 0 at the wall. When this expands or contracts, it's only going to happen here at the far end. Why is that important? Gibran still believes in you, Ellie. Okay, why is that important? That's important because when we set this up as differential equations, which we will have to do in the future, that's a boundary condition.
So is that like a?
Sounds like it's a lot.
Gibran says, Ellie, I still believe in you, and then left. All right, it's going to become, right, how many of you have had DPQ?
Working on.
You guys are working on it. Okay, all right. So in DiffyQ, we always try to solve where we can put things equal to 0. All right, because if it's 0, then stuff goes away for us, right? So we're not going to see deformation at walls. It's going to be 0. Now, when we when you guys build buildings and bridges, you're going to worry about this? Yes, you're going to worry about this. Okay. All right. But we don't necessarily have to worry about it today. All right. we will look at when we start our next one. Our next one we're gonna have to do is when we're varying loads. And, well, we'll do probably another one of these. And then we'll do one where we're also varying materials. Okay, yeah, we'll do the bronze and, steel one. That's a good one. All
Dr.
right,
Minky?
where we're varying materials. If I'm varying materials, what's gonna have to change?
The E.
The E is gonna also change, but we can then sum them up, can't we? Okay, we get into trouble when we can't just cut them into segments, so to speak.
So like smooth transitions. They're curved.
All right, so how are we feeling?
Taking it.
Gibran has a question. No, he doesn't, because he left the meeting. Oh, he's back.
So it fell.
All right, why for segment 2 we use 12? Because when we were looking at segment 2, we were looking, oh, you mean segment 2 or segment 3? So we have to think about this, and this is a good question, in 3 different ways. One way is, what load am I seeing? All right. Then, well, the thing said you left the meeting. Then, what load am I seeing? So the only reason we use 12 is because we were told in the original problem that between where B happens and C happens, that's going to be 12 inches. All right, we're only interested in the 12 inches part, but it's seeing that 30 kips load on the end. You can't get rid of it. It's more of perspective. If I am sitting in the green area, I'm not seeing the blue at all. And that's why we then didn't worry about that. All right, because we're making an assumption that this 30 kips, it doesn't matter where we are along here, we are still seeing an axial load of 30 kips. Okay. All right, guys. So here is your second 10-minute break. If you are online, I will email some stuff out to you. Would you like, kind of worried about, but would you like us to go ahead, exam 1 you want on chapter 1, correct? Or should we introduce prismatic segments? Okay, we'll do prismatic segments for chapter 1. Next week, we're gonna have to get into really ugly deformations. And so that we might want to wait on that. Because we're going to be, I think we have to start doing intervals. All right, so we might wait on that, but we will talk about it next week. There is a preliminary exam 1 review. I will then adjust it. Yeah, you'll have to send me an email and I can do that. I can't send you the homework. You'll have to get a book. D2L isn't messy. D2L is working just fine. All right, so that is, we'll go ahead and call class. If you're in class, you need to make sure before you walk out. And if you're online, I will post it all for you. You need this as group work, right? You need this quiz 1.7 where I gave you the equation sheet twice because I assumed you would rip it off. You're going to pretend this is proctored, meaning sit down and do it without anything. All right. And then here is the start of the sample exam review. So you guys can start in on this. And we will add in some more information then, and I will get that posted for you. All right. So you guys have a great evening. I will post this video once it renders, and I will see some of you on Monday and some of you on Tuesday and some of you on Thursday and some of you on Wednesday. All right.
Dr. Minky?
Yeah.
I was just wondering when Tuesday's fluids class was going to be posted.
Oh, just send me an email and remind me. I just forgot to transcribe it. Honestly, I got home Tuesday and just sort of collapsed.
Understandable.
All right, very good.
Thank you.
Thank you, Dr. Mickey.
Yeah, we'll see you on Tuesday.
Oh,
Tuesday. Good weekend, guys.
Thank you, you too.
Who's mining crew?
You, Mayor Cities.
I'm calling them cities.
What do you call it?
I don't call them. I call them hay.
Thank you very much.
You're welcome. So you guys who are online, you are dismissed. Enjoy your weekend. Do some homework.